Okay, in this class I'm going to use the differential equations again to generate the master equations of kinematics. And again, remember that the second derivative of displacement with respect to time is acceleration. And if I let v equal the first derivative of position with respect to time, which of course we know it is, then dv dt is equal to d2s dt squared. Okay. However, if we look at using the chain rule as well as the v substitution here, d2s dt squared is going to be written as dv dt I can find by multiplying ds dt by dv ds. ds's would cancel here to leave me with dv dt. But ds dt, remember, is exactly v, so I can write that as v dv ds is equal to d2s dt squared. So I can use this substitution to help me solve this equation. So that's what we're going to do. So again, we're going to assume a constant acceleration. Let me get rid of these definitions just for the moment. Constant acceleration, that's important, of a, and an initial velocity of u. U is a constant as well. Initial velocity means the velocity is u when the time is 0. That's what initial velocity means. So what I'm trying to do is I'm going to try to solve this differential equation. d2s dt squared equals a. If the second derivative of position with respect to time is a constant, what happens? Okay, and I'm going to use the substitution v dv ds. So I'm using v substitution together with the chain rule is equal to a. Okay, v dv ds is equal to a. And v dv ds, remember v is ds dt. ds dt times dv ds would be dv dt, and dv dt is a. But we're using this substitution. So v dv ds is equal to a. Separate by multiplying on both sides by ds. A times ds. Okay, now I'm going to integrate on both sides, taking antiderivatives. I can factor out the a here because it's a constant. On the left hand side, the antiderivative of v with respect to v is v squared over 2. The antiderivative of 1 with respect to s is s, so we're going to get as. And we're going to get plus the constant of integration there. Okay. But what do we know? Well, we know our initial conditions are that v is equal to u when t is equal to 0. So using that substitution, therefore, v is equal to u, plugging in u for v, I'm going to get u squared over 2 is equal to plugging in t equals 0. Well, t doesn't work in here. T isn't given in here, but we do know v is equal to u when t is equal to 0. And when t is equal to 0, the displacement is always equal to 0. Okay, so v is equal to 0 when s is equal to 0. So I'm going to plug that 0 in for s. So a times 0, which is just 0 plus c. So you get c is equal to u squared over 2. Remember, when the time is 0, the displacement has to be 0 because displacement is change in position. There can be no change in position if there's been no change in time. Writing out my particular solution then, v squared over 2 is going to equal to as plus c plus u squared over 2. Doubling on both sides, v squared is going to equal to 2as plus u squared, subtracting u squared from both sides. V squared minus u squared equals 2as. And that's another one of my master equations that we've spoken about so far. And again, it depends on a constant acceleration and initial velocity of u. So if we know the acceleration is constant, we know the initial velocity is u, well then v squared minus u squared is equal to 2as. the final velocity squared minus the square of the initial velocity would be twice whatever that constant acceleration is times whatever the displacement is. And that's always constant acceleration where the initial velocity is u. Okay, so there's my master equations derived, and we'll be using differential equations to solve different kinds of word problems as we move forward. Okay, so practice that, make sure you can understand it, pause it, can you do it yourself, go through it, look at each step, make sure you understand each step. If you can get your head around that, that's going to be really advantageous to looking towards more complicated problems. Okay, practice.